Related rates problems are tied into the idea that different rates that depend on one another are occurring at the same time. Say you're filling up your swimming pool and you know how fast water is coming out of your hose, and you want to calculate how fast the water level in the pool is rising. Now you know one rate, how fast the water is being poured in, and you want to determine the other rate, how fast the water level is rising. These rates are called related rates because one depends on the other. The faster the water is poured in, the faster the water level will rise. In a typical related rates problem, the rate or rates you're given are unchanging, but the rate you have to figure out is changing with time. So you'll have to determine this rate at one particular point in time. Let's look at one problem to see the process. And the process in this one is using the infamous falling ladder problem. As you can see by the problem, a 13-meter long ladder is leaning against the wall, and it begins to drop down the wall. That causes the bottom of the ladder to shoot out at a certain rate. What we want to do is find out at what rate is the tip of the ladder falling down when x, or the distance from the wall, equals 5. So the first thing we do is set up a diagram. And in that diagram we show the variables x and y, which is your distance, both from the wall to the bottom of the ladder and to the top of the ladder. We also show the length of the ladder. After we've done that, we can include any other information in the problem, such as how fast the tip of the ladder is moving away from the wall, which is 2 meters per second, and when that occurs. As it turns out, because this is a rate of change of meters per second, we can call that dx dt, or meters per second. We are trying to find how fast the tip of the ladder is dropping, and so that would be dy dt, or the rate of change of the y distance over time. Now that's going to be step 1. Step 2 is to determine exactly how these variables that you started with, x and y and 13, are related. And this looks pretty much like a right triangle, so we could use Pythagorean theorem. You'll want to pick an equation that is the most obvious in the problem, and in this case these two are related directly by the Pythagorean theorem. After you've done that, then you want to differentiate. When you differentiate, you want to use the implicit differentiation approach. So we set up everything with respect to t, and t is always going to be what we're going to build this on. So it's going to be d dt of x squared, d dt of y squared, and d dt of 13 squared. You don't plug in any numbers until after you've done a full differentiation process. Now you can treat this just like the chain rule. In fact, it is. Implicit differentiation says that x is the baby. So we're going to say overall there's something being squared. The derivative of something squared is 2 something, and then the derivative of the baby is dx dt. The same thing with this one. We have a baby squared, so it's 2 times the baby, and then the derivative of the baby with respect to t. And the derivative of a constant is 0. Now we can put in all the information that we have that's been given. We know that we're looking for a specific moment in time, which is when x equals 5, or the distance of the ladder from the wall, that distance being 5 meters. We know what dx dt is because that was given to us, that the tip of the ladder moves away from the wall at 2 meters per second. And we can also figure out that y is equal to 12 by using the Pythagorean theorem. Usually one of your variables won't be given, but by using the original formula, you can figure out what that variable's value is at a specific point in time. The specific point in time is x equals 5, so by using triples here, I have a 5, 12, 13 triangle, and so y is equal to 12 meters. Now I can take my derivative equation and plug in all the numbers and all the values that I know. So I know what x is, it's equal to 5. I know what dx dt is, it's equal to 2 meters per second. I know what y is, it's going to be equal to 12, and I know dy dt is what I'm trying to find. Now I can isolate dy dt, and when I do, I'm going to get 24 dy dt equals negative 20 by moving 20 over to the other side, and then I can isolate dy dt further, and when I do, I get negative 20 over 24, or negative 5.6 meters per second. Now you're not quite done. You need to write this out as a full response. And the way we do that is by using the acronym WUW, or WUW. This first W is for what it is you're trying to find, the U is for units, and this W is for when it occurs. So we're going to write out the what part by saying what it is we're trying to find, that the ladder is falling at a rate of, then we put our answer, 5, 6, we put our units, which is the U part, and then we put down when it occurs, when the ladder is 5 meters from the wall. W, U, W. And that's how you'll do the falling ladder problem.